which maybe is not important, but yeah. Yes. So I was writing, yeah. So firstly, let me just clear this thing that this does not imply that f is decreasing, because it could be like this, and you can easily construct examples. Okay. So this is a good thing to think about, and this is not hard. Find an example. This is not related to the problem, which is non-monotonic. Not this will not help. It's not related to the solution, which is non-monotonic. Actually, find it. Like find a good example, like a like differentiable and so on. Okay. So now coming to the question, this one. Let us think. Yeah. So you want to show this, so then you can. No, this is not difficult, right? Can anybody think of how to approach this? This may not be that difficult. Wait, no. I'm not asking for this example. This is a homework. This you can think later. Okay, this is not for now. But the problem, the actual question, how do you show that there is a C where this happens? No, this is derivative is there. Yeah, because this is a there is a derivative. Yeah. Okay, so we can maybe consider. Right. Right. No, that will usually not help because that's a very local, that's the definition is for a point. Okay, so if we take a function like, once again, if you take just this function, why will this function not work? So if we take this function, so g of 0 is 0. So you understand why I'm taking this function, right? Because the derivative of this function, okay, you've tried that function. Oh, okay, okay. If you just take g of 0, okay, but let me just think. One second. So this is true always. Okay. But yeah, they are equal also. Yes, because it's differentiable given, right? So it's uh, no, it's all differentiable, all differentiable. One second. Yeah, this will. So the we know that, so you can also say that limit fx extend to infinity is equal to 0. It is the same as that of e to the power minus x. Yes, yeah. So you can use sandwich theorem. It's just in the picture, or you can. Right? So fx. Yeah, so we can. So we are saying that limit gx as x goes to infinity is 0. And also we know that gx is always less than 0, less than equal to 0. That is given. And we want to show that the derivative of g is 0. Now here is the one thing. Now we should try to draw a hypothetical picture of g and see if we can say something. Okay, let us try. So here is this. So you understand. So and we need to show because these are some kind of extensions of these theorems which like you will not get directly but need to show g dashed basically you need to show there is a horizontal tangent. If we try to hypothetically draw g, so g is something that is, see, it is 0 at 0. It is 0 at 0, that is important. It goes to 0 as x goes to infinity. Okay. Usually we don't do this technique. We never, when we take the function, we just try to see, we just think on like a J level thing. Let's try to apply means Rose theorem. But now just take some time. Try to draw the picture. I'm not doing it because just do it for yourself. Try to draw a picture of G and see if you can at least geometrically see that there will be a horizontal tangent. Then proving we can do later after that. So try to geometrically see what G is, how G looks. G must be greater than -1. That is G. Yeah, right. Yeah. Yes, that is always also there. Though that may not be useful for this problem, but it's an important thing. Yes, just just try to see it. Try to put the value of this G, right? So he's using the lower bound greater than, oh, sorry. No, that is, so how is that coming, Adish? Mm, yeah, it's coming, yeah, because yes, it is, or is it, so it is bigger than this, right? So maybe he's using, so you will something, so, okay, you're saying like this, oh, you're using this, okay. Sorry. So if it is, okay, yeah, so something. No, but it's positive. R is, it's from positive R. It's from, yes. So it's a very interesting thing, right? That it is 0 at 0, but then it's asymptotic to x equals to 0, right? But in a very interesting way, yes, asymptotic to y equal to 0. Yeah, basically, yeah, right. Asymptotic. This just means asymptotic to y equal to 0, right? So we understand what this means. It. So now just to complete the picture, right? Gx is always less than equal to 0. So gx is always below, but then it's asymptotic, which means it has to look like this. Does everybody agree? Right? It has to look like this. Now, do you see a horizontal tangent? So that is the thing. It has to be there. And this is not, this doesn't come, now you may say this is an infinite extension of Rolle's theorem, but then there are infinitely many extensions, right? But simply put, if you draw the picture, then you will see it. So this, now how do you, obviously we have not proved it. Okay, this is just a, now how do you prove it? Yeah, let's think about that. So think, I'll just write the things which we have discussed. So is this still here? Is it clear to everyone that geometrically there is a horizontal tangent? Yeah, Raghav and Chandan. Is it okay? Geometrically. Okay, then that's good. Now we need to prove this. Minimum position, right? So you have to just prove that G has a minimum. That's it. You have to prove that G has a minimum. So prove that G has a global minimum. That's, and obviously at the minimum, obviously we know derivative is 0, right? That's a good, those are the good places where derivative is 0. That's why we study derivatives. Prove G has a global minimum. It has an asymptote on this side. And this reminds me of one M math question, the first subjective question of some time back when I had written the exam, where that it had both side asymptotes and they asked you to show there is a global minimum. And I discussed this in class earlier with those. Okay, yeah, then that is that is more than sufficient. Yeah. Then it's also good. Yeah. Okay. Okay. But CMI they keep changing, but the ISI you can, yeah, relatively describe, more or less describe. Okay, so why will it have a global minimum? So remember, continuous functions have minimums. Continuous functions on closed sets, closed intervals for us. How? So what is the maximum minimum theorem you're referring to? You can use that. That is the extreme value theorem. Whether you have proved it or not, that's not important. I mean, that is not important here. Though if you would have, if one has proved it, understood the proof, then then they can do it. Okay, okay. Then try to use the idea maybe. Yeah, so I'm not writing it. I'm just saying extreme value theorem. But extreme value theorem applies to intervals. And in this case, this is closed intervals. In this case, it is not a closed interval. So then how do you do it? Maybe let me then leave this for homework. It means just try it because it's not hard from here. And you should just think, okay, so yeah, try to complete. Otherwise, I'll surely do it next time. It's very simple from here, but right. You can, yeah. So basically, the extreme value theorem says that continuous functions on closed intervals, the image is also a closed interval. Okay? But this can be extended to infinite intervals in the case of asymptotes. That's the general principle you can understand. Okay. That in the case of asymptotes, it can be extended to infinite thing. Okay. So this thing about like eventually the behavior is understood, and so you can cut it and understand in between also. This reminds me of a question which you can think about. This is a good question, I think. Let f f be a polynomial. Let's say R to R, real variable polynomial. Okay. Prove that f is eventually monotonic. Let me just say injective. Okay. This is not at all difficult. The difficult version is this is just to understand the. Okay. So what do I mean? I mean that so after a certain finite, outside a certain finite interval, it will be injective. Is the question clear? So f, if you consider f outside this thing, then this is injective. If you restrict f the polynomial to that outer portion, okay, it will be injective. Mm-hmm. Something I'm not saying that is the interval. You may be right, but yeah, some interval you can delete. And I'm not asking for the interval, but I'm just asking that just so that there is some interval that you can remove, such that you become monotonic, which is like the last problem, which is like what you started with, kind of. It's eventually monotonic, eventually also happened, eventually asymptotic, eventually zero. This is similar, and they're all related in some way. But this is easy. This is a question which is of fundamental. You see, polynomials from reals to reals are not such good things. They are not such good things. uh, for several reasons, because like a lot of different polynomials have the same set of roots. Like x square plus 1 has empty set of roots, x square plus x plus 1 has empty set of roots. So the set of roots and the polynomial doesn't really have a good connection when you are in reals, because not everything factors and so on. But polynomials over complex numbers are the actual things to study. Okay, and that's why I'm posing this question for complex numbers. Now you can think, is from C to C. Yes, that's what so I mean that basically there is an interval from the domain which you can remove, such that outside that interval, the polynomial is injective. Okay, and sorry, I mean odd degree polynomial. Odd degree. For even degree, it doesn't happen. Yes, yeah. Then it's not injective. It is like a 2-to-1 map, right? It's like a 2-to-1 map. Yeah, that can be said, but yeah, right. That's right. But here is the interesting question: if f is a polynomial from C to C, yeah, then C to C means C to C. Again, show that f is eventually inject even odd degree. Odd degree. Okay. Then is there a disk? Is there a disk D such that f, when you restrict f, or let me just, when you restrict f from the complex numbers outside the disk D, then this function is now not, that's why I didn't use monotonic, because if you use the word monotonic and injective are kind of the same things for reals, but they are equivalent things, but injective uses less structure, and so it can be used to generalize, and that's what I'm doing here to make this question is injective. Now this question is I'm not making a claim. This is I will not say what I think. Yeah. Try these two questions. These are think about it. Right. Okay. So yeah. So now let us, so you can note it down or you can see it later. I will put it on YouTube after maybe tomorrow or something, hopefully. So let's move to